So what we'll do now is we'll put the entire components right together and try and see how they orchestrate well together to accept reads. Oh, sorry, writes. So we've got a client. As always, the client gives the data over to the coordinator. The coordinator is going to do all the hashing and figure out that, hey, these are the IP addresses. And I'm representing one such IP address. I'm representing one single Cassandra node that is going to receive the data. And we know that in this particular node, we have basically two core components, memtables and commit logs. Commit log happens to be on the disk, and obviously memtable will reside in memory. And when you really look at this particular diagram, you can see that, oh, okay, so that means more the memory, the merrier, because it can then hold a lot of information in memory, and the frequency of dumping the data on the disk right periodically will reduce. That's one of the advantages. But anyway, let's do this. So the client hands over the data to the coordinator, which could be a put operation at this particular point in time. That's what we are talking about, right? And the coordinator is going to convert it into what is called as a mutation, right? The Cassandra class name is called as mutation.java. A mutation is nothing but the internal representation, the byte buffer representation of the data that is provided by the client. It is the mutation that gets transmitted across the wire and it reaches this particular node. So the first thing that it does is it appends it into commit log. I do know it says number 2 and number 3. You might be wondering what happened to number 1. I'm going to come to that. Right, so it appends to commit log, and then it goes out there and also puts it in the memtable. When we create a key space, we have something called as durable writes. If durable writes is not equal to true, then the commit log appending is not done. Only the memtable is updated. Hardly ever anybody uses the durable writes equal to false. Maybe there are some use cases that will require us to not write the data on the durable storage on the disk. Maybe there are cases out there, but for the most part, durable writes is equal to true. And that appends the file in commit log, puts it in memtable. Your write path is over. And that's the reason why writes are considered to be very cheap in Cassandra. And therefore, duplicating data, denormalizing data, etc. is really no big deal, because this is all what it does. And that's when the node is done, it responds back to the coordinator that, yep, job done. Now the question is, what happened to 1? Let's take a look. So if you define, other, components like materialized views, by the way, materialized views are not supposed to be used in production. And there are several reasons, for that. It was in, preview, then it went into production, then it did not deliver on the, points that it was supposed to. There were lots of problems. Now it has gone back again to preview. And it is discouraged, to be used in any, which way. The important thing is secondary indices. So when we create a secondary index, we do know that it is an internal table that Cassandra has to manage. So the moment the data is coming in a particular table, it has to ensure that if there is a secondary index, it has to go out there and update that as well. So that happens too. And the third part is invalidate the caches. Now this last point is very specific to the read path. So naturally, if you are reading data, Cassandra will want to cache the data in its memory. And if it goes out there and if the user updates that particular data, so naturally you'll have to go invalidate those caches. Now, what is the nature of the cache, etc.? We're going to take a look at the read path, but nevertheless, the write path has to go and invalidate those caches. So this is basically, the flow when the data is coming in from the client. The other important aspect to be kept in mind is the CDC, change data capture. Change data capture is also exactly like the commit log. The only difference is Commit logs are thrown away after a flush occurs, and I'm going to show you flush next. However, CDC is never thrown away. If you want to keep a logic or a chronological trail of your data modifications, if you want to find out that the final state of data is this, how did we get here? What are the changes that ever occurred on this data element? If you want to find that out, right, CDC is your solution. CDC structure is just like the commit log. In other words, it stores the mutations. You may have to write some custom applications to, read those mutations and bring it into your application, to make sense of it. But in version 4.0, there will be some utilities. There are some utilities which will allow you to process that data without having to, write some custom code. But anyway, the important part is the write path comprises of two major steps. Append into commit log and put it in the Memtable, and that's it, you're done. So naturally, over a period of time, what will end up happening is the Memtables will begin to fill up. The memory will begin to fill up. So what basically happens is when there is a memory pressure, and there are 4 other trigger criteria, which I'm going to talk about, Cassandra will traverse the binary tree of the Memtable, and it's going to throw the data on the disk. And this particular location on the disk is specified in Cassandra.yaml as a data directory. And once it throws the data on the disk, it creates a new generation SSTable. Remember, SSTables are immutable. SSTables, once created, will never be updated. So a new generation SSTable gets created, and once the SSTable is created, you really do not need the commit logs anymore. So it will go out there and mark all those entries that exist in the commit log as flushed. Needless to say, once all the items in a commit log has been marked as flushed, that particular commit log segment can actually be discarded. And you can move on to the next commit log or create a fresh commit log. So this process happens over and over and over again, right? So as a result, what will happen is you will see that the number of SSTables is beginning to grow on the disk. And obviously this contains the real data. So these SSTables are going to be the actual DB files, right? Which you want to, if you want to draw parallel to your RDBMS systems, the database files, SSTables are nothing but database files. The good thing is you can actually track the flush process, etc. You can actually find out, when the system is, dumping the data on the disk, etc. You can do all of that. One good thing is we really don't have to worry about it, right? Cassandra will manage this on its own. However, Cassandra does provide the tools to manually flush as well. The other aspect we need to keep in mind is if you have a very small memory, you can naturally, deduce that if that is the memtables will fill up rather quickly and it's going to flush often. And the moment it starts to flush often, the number of SSTables will grow very quickly. Small SSTables will be the result of that. So that's the reason why more the memory, the better. Let me also talk about the triggers. First thing is memtable total space reached. That means the memtable is full. When this happens, Cassandra will initiate a flush. Second, commit logs, total space in MB reached. In this case as well, because there is nothing else to append to, right? We are running out of disk space. Well, we got to free up. So this is another trigger where Cassandra will initiate a flush. And you can, by the way, specify all of these in Cassandra.yaml. You can manually flush it as well. So you can say no tool flush with key space and table as an optional variable, as an optional parameter. Once you do that, that initiates a manual flush. You can also force the tables to flush if you are taking a snapshot. So when you're talking about backup of node. I really don't want to use the word backup because backup means something else in Cassandra. You can actually back up an SS table the moment it is compacted and all of those kind of things, or it is flushed at the same time. So those are the kind of things are associated with backup. So think of snapshot is the equivalent of database backup. So if you want to snapshot a Cassandra node, you can issue the command called node tool snapshot, and optionally you can give the key space and table name as well. So obviously you can't really snapshot data that is sitting in memory. So Cassandra will initiate a flush that will create the SS table. Those SS tables are hard linked to a snapshot directory. And in that directory, what you can do is you can tarball the files in that and move it onto to a different location. So this will ensure that your data on that given node has been moved away. So in case of an adverse situation, your node going down, you're losing your disk, you can rebuild your disk from those snapshots. And by the way, the snapshot will contain the SS table. And the third one is, the fifth one is when your Cassandra node restarts after a failure, right? Perhaps it crashed. Perhaps we did kill -9, the process ID. Why would we do that? But let's assume we did do that, right? And you're restarting Cassandra, right? It's going to take a look at, oh, okay, I'm recovering from a crash. So let me rebuild the memtables, looking into the commit logs. And once it has rebuilt the table, it will initiate a round of flush. So what will end up happening is it will rebuild the memtable and it will immediately throw the data on the disk, right? Thinking that, look, I just recovered from the crash. I want to make sure that my data is in a location which is durable, which is long-term, which is persistent. And I don't want to really do this process again in case I were to go down. So this is something that was introduced, the point number 5 that was introduced, I think in version 3.0 or thereabouts. So the whole idea is client sends the data to the coordinator, coordinator sends it to the node, node appends it to the commit log, puts it in the memtable. Over a period of time, when memtable fills up, throw it on the disk, right, and the SS tables gets created. That's by and large what the write path is all about.